Now, before we continue, I would like to make one important point, and I don't know if this already occurred to you, but at least you might be inclined to think that it's rather obvious that the problem that Alice, Bob, and Carol are working on is intractable for one simple reason. Each of their problems has to look at an exponential number of solutions. So for vertex cover, we have O of 2 to the power of n potential solutions that we have to look at, because there are 2 to the power of n 0, 1 assignments to the vertices for putting the vertices of a graph into a vertex cover. And the same thing is true for independent set and click, as we have seen in the last unit. Now the question is, does the fact that there's an exponential number of solutions already mean that the problem must be intractable? You could basically think this because having to consider an exponential number of solutions might mean that you have to look at each one of those solutions, and that obviously is going to take exponential time. What I now want to show you is that this is not the correct intuition to have. So having many solutions does not mean that a problem is intractable. It can mean this, but it doesn't have to. And to show you this, I'm going to give you one example where we have an exponential number of solutions, but actually there's a polynomial time algorithm for our problem. So what I would like you to tell me in this graph here, how many different paths or how many different ways there are of getting from A to B if you cannot go backwards. So you start out at A, and once you've traveled across an edge, you cannot go backwards. You always have to go forward. So how many ways are there to get from A to B? And of course, this is a very simple warm-up example. And I'm going to draw little arrows here just to make clear that we cannot go backwards.